Morning. How's everybody doing this morning? I'm going to go ahead, if you don't mind, I'm going to go ahead and take the mask off. And we'll go without the mask since we're 6 feet in the room and everything, so we should be fine. I just passed the CEO this morning in our hallway here, and we both had masks on, and I just looked at him, and he said, "How you doing?" I said, "Good." He said, "Who is that masked man?" I said, "Yeah, there's silver bullets on the hallway. We all look like bandits and the Lone Ranger running around here, but it is the world these days, isn't it?" So we're here this morning back in the bunker again. We're going to talk about meter site design, and actually we'll go through the preliminary stuff like we always do, which is the talking about this is the COVID series. This is which number is this one? Oh, I got the thing. Okay, I get to do it. Cool. Ooh, I have the power. All right. So this is, today we're doing design and meter installation. Next Tuesday it's going to be standards, traceability, and accuracy. Have some smarter people talking about that. And then on next Thursday, you'll be stuck with me again. We'll talk about billing versus metering accuracy. That is we're going to play with it a little bit, maybe doctor a little bit. That's one that you've maybe seen at some of the meter schools, because we've been doing that one for a pretty good, we've been doing that one a long time. And so we'll probably doctor that one up and change it up a little bit. But that's what's going through next Thursday. If anybody's got any ideas, man, we'd love it. And we've used them already with some of what you guys have sent us. So send us some ideas and what you'd like to see. You can get very specific if you like. I mean, so because after a while, we're trying to come up with ideas. So if you could help us out there, we'd appreciate it. And so you see what we've got so far, so just sling some stuff at us, and we will definitely consider it. Here's what we're going to do today. So the objectives of the class are, we're going to be able to identify the main parts of a meter site. We're going to learn the basics about what must be considered for each piece of equipment, and then we're going to go over a real-world example of a meter site installation. So we're going to talk about what parts make up the meter site, and but then, like it says here, there's a lot of things to consider before you select all those pieces. Okay, so we're going to go over that, some of the criteria that you would use to select that piece of equipment for that site. And then we're going to actually go through an example and do some calculations and look what would be the best selection between the CTs and the meter and everything. So that's what we're going to do. So before we get cranking, I'm going to go ahead and pray real quick, and then we'll get started. Father, thank you so much for this time today. Thank you so much for just the technology and the ability to reach out to the folks that we really miss out there. Father, we miss our customers, and we miss our family. And part of the Powermetrix family, everybody that we deal with if they've dealt with us for as long as most of them have, they know how we are, and we miss them. We want to be in contact with them. We want to go see them. So, Father, hopefully that will open up here soon. And we've just got a lot going on in this country right now, Lord. So I would just lift up this country to you, and lift up the leadership of this country. And Father, there's just, from what we're seeing going on, it's just hard to see much of a Christian biblical lifestyle in it, and just loving one another. And that's what it's about. And so, Father, just help us to open up our hearts and our minds to what's going on, to listen to people, and Father, most importantly, to love our neighbor as ourselves. So thank you for the time today. Thank you for what we're going to learn and go over. And all of these things I ask, and I say, according to the will of the one who paid it all, my brother, Jesus Christ. Amen. All right, let's roll. So we've got what makes up a meter site. So you can see some of the things that they've got there. You can see your socket base over there. You see transformers, and then, of course, equipment to test with, CTs, PTs, and the actual meter. So we've got the meter socket, enclosure, test switches, instrument transformers, wire, power quality, and site test equipment, and of course the meter. So until you get out there and you really start looking at all the little bitty pieces and you have to really design one of these things, sometimes some of the stuff you just overlook, but some of these things are very critical to how you're going to design the site, and we're going to get into that here in a minute. So there are a lot of parts and pieces to it. If it was easy, anybody could do it, right? So meter selection. So first you have to decide on the service type and the meter form, right? So we've talked about this before previously. We basically fall into two groups, right, on the meters, self-contained and transformer rated. And so we know that the self-contained has no external CTs or PTs to it, right? So it's got some internal CTs, but the transformer rated has external CTs. So with that, we can go to a lot larger size CTs, as you're going to see here in a minute, which affects the amount of current that they can handle. So then you have, of course, the voltage and current rating. You have the accuracy of the meters definitely to be considered, and these are all things to be considered when you're going to select the meter. The measurement modes. Are you doing more than just watt hours? You're doing VA hours, VAR hours, demand. And then, of course, AMI compatibility, which that's been going on for years now, so AMI is absolutely something to consider because you would hate to have to get something in there and then it isn't AMI compatible. You have to literally change everything out versus a modification. So yeah, the compatibility on the AMI is definitely important. What makes up a service type? Okay, you got single or polyphase, right? So 2 or 3 phases, a delta versus a Y, and then a 3 or 4 wire, and then the customer demand determines how much current to be metered, right? So depending on the site, how much load is at that site, and how much current they need, that's definitely going to affect it, right? Because you're going to see here in a second, they fall into categories very quickly of how much current can that meter take. So if it falls above that, then you have to go to a different meter, right? And we're going to see all that here in a second. So the two electrical service types that we talk about all the time are delta versus the Y, right? So delta, you'll hear guys say it's pretty easy to recognize the delta, right? Because it's shaped in a delta, and then the Y is shaped in a Y. So, and you probably recognize the one on the right from Back to the Future. It looks a lot like that flux capacitor, doesn't it? The one on the right there. So 3-phase transformers, delta versus Y. Let's talk about it. So the delta is commonly used for power transmission. It only requires 3 lines, right? So the delta is better for balanced load like a motor and has greater reliability if a winding failure occurs. And the Y offers 2 voltages, line to neutral and line to line, and the Y is used when a single phase load is required. So what we're saying there is, looking at the delta going to phase, if for you to lose a leg, you would still have phase to phase, right? But if you lose a leg on a Y, then you're done. So that's one consideration of why people would go delta. And then the other is the cost, right? So that's one less conductor you're having to run. So it's both cost, and in those type situations where you might lose a leg, which happens with motors and stuff, then you won't be dead, okay? Now the Y offers 2 voltages, as you can see there. It says line to neutral and line to line. So the Y is used when a single phase load is required. And the Y is more popular, a lot simpler to wire up. Everything seems more clear. And I know from you and I, testing, I'd much rather test the Y sides than the delta sides. But the delta has its advantages, and you can see there why. So service type and meter form. So yeah, there are over 30 types of meter forms, do the many kinds of connections, but we know now that all the utilities they're pretty much, because they're much more robust and flexible with the electronic meters now versus the old electromechanicals. So now you can cover a lot more services and service types with the same meter. So we're starting to pare that down. So the typical utilities, you guys typically only have, maybe 4 or 5 different meters that you use, okay? So you can see the service type will determine the meter form, and the modern meters can be set up for many forms, like we just said. So typically only a few meters are used by the utilities, and that's what I see. What I run into out there, though, is stuff that's still out there on the line, but you guys have been changing them out and changing them out. So you're seeing less of that and less of that and less of that, and as those numbers are paring down more and more. Here we got a little chart here. If you ever want to use this, here's this just common meter forms. It's showing first the self-contains. It's just giving you a chart there showing 1S, 2S, 12S, and 16S. And you can we're showing on the 12 and the 16S there, we're showing both the Ys and the deltas, because you can have a Y or a delta with a 12 or a 16. Okay? And notice over to the far right there, the class. Okay? That's your current class, right? So that tells us what current they can handle. Okay, over on the far right-hand side, which is going to definitely, when we start designing the site and making our choices of the meters, that is going to be one of the critical criteria there is how much current they can handle. Okay? We get to the transformer rated. We got a 3S for the single phase. We got 5S, 6S, 9S. So in there you can see there the class says 20, but remember that's just the meter. We're not talking about this. You're going to have external CTs and PTs, which are going to bring it down to that point so that the meter's only seeing 20 amps. Okay, but the actual service can be a lot larger than that. Okay, so we can just upsize the CTs. So you got self-contained versus transformer rated meters. And so the transformer rated, you can go up to 480 volt, typically 120 volt. Most of the meters you see out there now are the multi-range meters, right, where they'll go, you'll see on there, say 120 to 480. So it can handle anything between 120 volts all the way to 480 volts. Okay, and then the current up to 20 amps at the meter. And we know that because we've talked about this previously. We know that it's 20 amps there because the test switch that's right there feeding the meter, that is rated 20 amps. So everything on a transformer rated site down there at the actual meter installation, the meter, the test switch, and that, it's all rated 20 amps. So to get it down to the 20 amps, the next point says it requires CTs. Because if I've got a 1,000 amp service out there, I've got to get it down to 20 amps. Because remember, we've talked about this before, that's what's available at the bottom of the pole. All the smaller rated stuff, so we can make everything smaller. The little test switch and stuff, we don't have to have big blades to handle 1,000 amps. Or any kind of interrupters or anything for you to be able to work on that stuff. So we transform it down to the 20 amps. You can also use PTs as well to bring that the voltage down. You can bring the current down. You can also bring the voltage down. Just right up in that first line, it says 480 volt, but typically 120 volt. So we know a 4-to-1 PT right there would take 480 volts, and you would have a fourth of it down there on the secondary side, so you'd have 120 volts. So you could use a 4-to-1 and take you from 480 volt to 120 volts, down to 120, which we like working with a lot better than 480. And then, but it is higher cost due to more equipment because you're having to add the CTs and the PTs and this other stuff, right? And plus, as you're starting to add these components in there, they all have an accuracy level themselves, right? So all of them have, and with an accuracy, they also have a level of inaccuracy. So each one of these levels of inaccuracy that you're adding to it accumulates, so you tend to have a lower accuracy due to those instrument transformers. So self-contained. You got voltage up to 480 volts, and the current ratings are 100, 200, 320, or 400 amps. So, and for a K base, you can have current up to 480, continuous 600 amps max. So it does require a larger gauge wire because remember 20 amps on the transformer rated. So you got gauge wire, 20 amp gauge wire versus here you can see these numbers. So you're going to have larger gauge wire. It does not require ATs, so it's basically less expensive. And remember, I'm not adding those little levels of inaccuracy in there with these other components. So you could say that it is more accurate, the self-contained is. And like I said, it doesn't require those instrument transformers, so it's less expensive. And but the limitation is on the amount of current, right? Because my CTs, if I have them, are internal in the meter. So I can't do anything to help by adding some external CTs or anything to it. So I'm very limited in how much load I can handle. But they do tend to be less expensive installation, and they tend to be more accurate. Okay. So how much current? So let's look at an example here. So we've got an example of, because remember, current's going to be critical on this because we have that break line, right, where you can only go so high in current with those self-contained, and then I'm going to have to go to a transformer rated. So the amount of current's important. So let's look at how we get that. So we say, we got an example here. We've got 277 480 volt, 3-phase, 4-wire service. We've got a 750 kVA transformer, and we've got a current per phase. You say, if you're looking for the current per phase, which is what we need to find, you're going to take the total site power divided by the number of phases divided by the voltage. So in our example here, it was 750 kVA, right? So that's 1,000. So that you have to put that 1,000 in there. So that's why it shows 750,000 because it was kVA. So you have to, add the 3 zeros there to go by 1,000 because that is a 1,000 factor with the K. So I've got 750,000 divided by 3 divided by 277 gives me 900 amps per phase. So now what kind of meter will we use, self-contained or transformer rated? Well, remembering our limitations on the self-contained from the previous slide, you should say to yourself, I think I know the answer because I'm over 600 amps, right? So it says here, did I go too far? So you would go with you would have to go with transformer rated on that one, right? So let's look at the meter accuracy. So because that's the other consideration, how accurate do you want the meter? So the accuracy ratings are 0.5, which is typical on your resi meters, and then you have 0.2 or 0.1 on your electronic meters and that are the transformer rated, okay? And the self-contained can get up there too. So, but 0.5 is a typical resi accuracy. So the transformer sites may require a higher accuracy meter due to the instrument transformers on there. So because my instrument transformers are providing me that accuracy, then that, it says right here, transformer states may require a higher accuracy meter due to the instrument transformers. So if I've got some of those extended range now and I've got some like 0.15% accuracy CTs, then you see what's going to happen, right? Then I need to make sure that my meter matches up, all right? And there's no really standard for VAR and VA. You've got harmonics and power quality can affect the meter accuracy. So another consideration would be, is this going to be an installation that's going to have a lot of harmonics involved in it? That's another thing to consider, okay? And before you choose your meter. Meter measurement modes. Of course, the early mechanicals, it was just watt hours, right? But on the solid state meters now, you can measure a lot of different things. We talked about it earlier, VARs and VA and everything. So the meters can be programmed for these different modes and outputs. And we do have, excuse me, they also do have some advanced functions now of the power quality and harmonic analysis. We know harmonics have been the buzz for a little while now. So we are trying to recognize the issues for harmonics, and the ANSI committee has been talking about it a lot. So you've seen more and more of an emphasis on the harmonics. So you can see that they've got it. So the meters are following suit with that, how important the harmonics are, especially maybe in upcoming standards that might be coming up in the future. Because you would think with the emphasis on the harmonics, we're definitely going to have to take that into account from the testing side as well. And we've already started working on that as a company because we know that eventually it's coming on the harmonics. So you have the AMR, or automatic meter reading, and then you have advanced metering infrastructure, AMI. So AMR is, much more AMI now, of course. It was the earlier technology was AMR. But there are many communication options, and all of this has to be considered when you're selecting your meters, right? And selecting these meters when you're designing the meter sites and you're doing a major meter change out. Everybody sits down and considers all these things before they make the selection, right? So they're going to consider, how are we going to communicate with the meters? Ethernet, cellular, power line carrier, RF, modem. So then you have the different the kinds of connections. You have pulse outputs, the 232, the 485, and then you need to check what type of AMI or AMR support is required by your utility. So remember, there's two sides of it. There's their support, but there's what do you have to do to support the AMI or AMR on your end, okay? And all of that has to be considered when you're selecting your meter. Then you got to put the meter in something. So we're going to select the meter cabinet. So lots of different shapes and sizes. Thank you, Durham, there. And I better say something real quick. You noticed maybe on the front page it said John Jones. I mean, if anybody knows it, they're probably like, really? No, this was Steve Hudson did this. Steve Hudson put this presentation together. Steve is head of engineering for Powermetrix for us. You've probably seen him at the meter schools. He does a great job of teaching all these classes. And a lot of these presentations you're seeing now, Steve is doing the lion's share of the content on them. So if you've had a chance to talk to him, he's got a lot between his ears. He might be a guy, if you ever see him at the meter schools when they get started again, is grab Steve Hudson if you got any questions, because there's a lot floating around in there. So he's got a lot of knowledge, and he is basically the head of engineering for Powermetrix. So if you think about it, the 3 series, the benches, these are all, he was the brainchild that drove all those things, and with the other engineers we have here. So this was Steve, and so I appreciate doing his presentation for him. But if you get a chance, when the meter schools get back going again, or if you just have something serious you want to ask a question on, call in here and ask for Steve Hudson, because when you really get down to it, like I said, Steve is very knowledgeable when it comes to this stuff. So selecting a meter cabinet, you got self-contained or transformer rated, of course, as we said in the very beginning. That's going to dictate what kind of cabinet. The current rating, it's always important. We keep seeing that, right? Because the current rating is the delineator between self-contained and transformer rated, right? So that's going to, the second one affects the first one. So once I know what current rating I have, then that's going to be one of the keys to tell me self-contained or transformer rated. Then the number of terminals that you need, the socket type, pad mount or pole mounted. That's also a key. They've got some pretty slick cabinets now that can be mounted both pad and pole mount. They've got these combo cabinets now. And then, of course, gang sockets. If you've got an apartment complex or something like that, I've got my main service disconnect, and I've got a whole bunch of sockets there. I've always got my main entrance, my SUSE entrance point there, where I have my service entrance, but then I could have a whole gang of meters behind that, right? Self-contained meter cabinets. Typical currents on these are going to be 125, 200, or 320 amps. You've got 4, 5, or 7 terminals depending on the meter form. Those will take care of all your self-contains. Then you've got lever bypass for easier testing and also safety. And then you've got, once again, the gang sockets for the apartments. So you've got lever bypass. It's a easy install removal of the meter. And it's a bypass the power during the meter testing, and then more expensive and larger cabinet. Okay, this all boils down to it's the ease of removal of the meter, much easier and safer with this lever bypass, okay, because we know that we've bypassed, like it says there, you bypass the power, so I can feel a lot safer removing and installing a meter when I've got the lever bypass. There's always the other side, right? So there's the expense of, it's going to be a little bit bigger cabinet, and a little bit more expensive because of the bypass hardware in there and everything. So it's always, you're going to weigh that when you're making a choice, right? You're going to weigh ease of testing and the safety on that versus the cost. And it's always the battle when you're trying to design this stuff, right? So you guys will sit down and talk about it and come up with it. And then the gang sockets here, so you can see a picture of that. You can see I've got to the far left there, I've got my entrance there. We're going to come in with my feet, and then I've got all these, and each one of them, you can see the little black box to the right of the round sockets. So that's usually a disconnect right there. So I've got my SUSE. If I got 6 throws of the hand, right, I don't have to have a main breaker in the beginning of it, according to SUSE. Service use for service entrance, suitable for use of service entrance, excuse me. So what it tells you is I got 6 throws of the hand, right? So if this is going in somewhere, if I have more than 6 throws of the hand, and this goes all the way back to the days of fires, you know, if you think about it, what we see today is developed because back in the day they just had bare wires running everywhere, and the fires were the main problem with trying to first run and use electricity in our country. So the main thing was how many throws of the hand so I can shut everything down, you know, if a fire had started. And that's, if you go way back, that's where they came up with 6 throws of the hand. So here's a case where you can see if I got 6 throws of the hand or less, I don't have to have a main in that far left side, okay, according to Dancy and SUSE. But if I had more than that, I would need to have some sort of a main breaker or main disconnect on that far left. Transformer rated meter cabinets. So here we got our good old test switches there in the bottom of it. You can see right below the meter there. And so they're rated for 20 amps. You can have, now we're going all the way up to 13 terminals with the transformer rated. And then the larger cabinets for the CTs are available. So you've seen the seat where you open up, then actually the CTs are within the cabinet as well. Okay, so that's what we're talking about on that last point. That's what Steve's bringing up right there, is you can have cabinets with the CTs within the cabinets, or you can have an external where you just got just a CT cabinet, right, sitting right beside the meter can. So you can do it different ways. But the important thing for us is it's a lot easier to work with those test switches when you're testing transformer rated meters, right? Yeah. So with those test switches now, you can see there, they allow for easy testing of the meter and the CTs, and the meter can be bypassed without interrupting the customer's service. And that's a biggie, okay? When I throw those shunts right on there, it just shunts across, but it doesn't disconnect anything. So I can still, I'm just reading. Remember, with our test equipment, we're going in just in series, okay? We're not interrupting anything. We're just inserting in there so we can still see that same flow of that current going through there. We just want to insert our duct bills in there in series so we can get a flow into the equipment and back out of the equipment, but continue through the circuit. So you can see in this example over here to the far left, you can see that you've got, you can tell by the throws of the blades too, can't you? You can see a long throw of the blade with it's just a straight blade, long throw of the blade, nowhere to insert a duct bill. Those are going to be your voltages, right? So you can see over here the voltages are on the left side of this test switch. And when I got those little short stroke switches on there, I know those are going to be my shunts because they don't open fully for my CTs. And then I have the return. So I got the shunt coming and feeding in from the CTs, and I've got the return going back to them, and that's when I've got that longer stroke blade, but it's got that cross in there where I can insert my duct bill in there, okay? So what is an instrument transformer? Well, you can see up here in the example we've got over here where the red arrows are, we've talked about this a lot, and it's very important to you and I from a safety standpoint, and the size of the equipment we got to deal with at the bottom of the pole is they take high levels to lower levels. So we always deal with step-down transformers, typically. And so in this case, as Steve's put here, instrument transformers convert signal levels from dangerous or high voltage or inconvenient high current or current at a high voltage to levels appropriate for meeting. So the two step down, like I said, typically step down transformers that we use are CTs and PTs. CT for current transformer, PT for potential transformer, which is going to be our voltage. So like we mentioned earlier, the numbers are, it takes a primary and drops it down to a secondary. So as we said earlier in that example, we had 420 volts. We wanted to get it to 120 volts. So we needed to have a fourth of the 480 to get to the 120. So if I have a 4-to-1 PT, it says whatever I have on the primary, the secondary is going to be a fourth of that. So if I have 480 amps, 480 volts on the primary, I'm going to have a fourth of that, which is 120 volt on the secondary, okay, coming out of that PT. So, and the same thing works with the CTs, okay. We have that primary we talk about a lot. I got a primary to a secondary ratio. Okay, so if I have a 200-to-5 CT, that means the ratio between my primary and my secondary is 200-to-5 or 40-to-1. So that means whatever current is coming through that primary side, you know, I'm running it, let's say if I got a donut CT and I run the current through there, whatever that current is running through there, if it's a 200-to-5, you're going to see a 40th of that coming out on my secondaries on my CT, okay? Potential transformers, PTs, we just talked about a little bit. They're going to step down the voltage, and like it says here, you usually want to have 120 volts, sometimes get down in the 60s, but most of the time you're trying to get to 120 volt. So if you've got, like we said, a 480 volt and you want to get to 120, you would just get a fourth of that and you use a 4-to-1 step down PT, okay, transformer. And yeah, they got a lot of shapes and sizes of them. Remember, we talked about this in our last class where we talked about the testing of the PTs. We said that they're rated in VA, okay, so that's what you have to look at on them. And the VA rating must be determined at how much power will be drawn on the secondary. So you rate them off the amount of power there, the VA, okay, is how they're sized. They come in various accuracy classes. However, the 0.3% accuracy class is generally used in North America. Now remember earlier we talked about the levels of inaccuracy added in. So remember, you're now adding in 0.3% accuracy. You're adding in some more. Yes, it gets it safer and stuff for us down at the bottom of the pole, but all these things we're adding in there in a comparison between transformer rated and self-contained. You are unfortunately adding in some more inaccuracy, but it's making it a lot safer and easier to deal with. And you have to when you have that size of a load and that big a customer, right? When I got that much up there, running up there, I can't use a self-contained. I need to use transformer rated. I've got to get it down to a safer level that I can actually meter and then I can test and work on. So you kind of, when you're doing it, you can see that even though I'm adding them in and making everything safer, unfortunately I'm adding some inaccuracy in there. That's why we test them. So current transformers, CTs. You see the ones at the top, those are the donuts mentioned earlier where you can just run the conductor through those, the hole of the donut, right? So you can run in through on those top ones. You also see the bar type right there, okay, down bottom left. And you know when you guys have used our equipment and done a load boost test, that's why in the load boost kit it's got the clamps as well as the drive cable, right? So I know there's some people nodding out there. So when you run the drive cable through it to boost it so that I can go to a dead site and I can still test the CTs, I would use the donuts, right? So I'm going through the donuts and I can use a drive cable. But if I have that bar type, I can't. So that's why we also have the clamp-ons in there so you can clamp onto to those bars on either side. Okay. And here's some, you got the, all this stuff's on the nameplate there for the CTs. You can see where it shows the accuracy class down there. It says 0.3% accurate, right? And we're going to talk about it in a second, but it says it's 0.3% accurate, but it says at 0.1, and we'll talk about that here in a minute. We got the ratio, which we talk about a lot. So the ratio for this CT is 100-to-5, okay? So it's 20-to-1. So this is so what it's saying is the ratio is if I see 100 amps primary run through there, I'm going to see 5 amps on my secondary terminals, okay? We got the rating factor there. We're going to talk about that here in a minute. If this is 100-to-5 CT and I have a rating factor of 3, I can actually I can put 300 amps on that CT. Okay, and we're going to talk about that more in a minute, the rating factor. And then primary voltage, it'll tell you what voltage this CT's made to run at. And then you've also got the secondary voltage. It shows you over there on that left side. So we talked about, these are some of the things we just showed on the nameplate. So the characteristics of the CT. Ratio, the primary to the secondary ratio, like we said, 100-to-5. So that's the ratio between primary and secondary, 100-to-5. The accuracy is measured in percent for a rated burden. But you saw that a minute ago, it said at 0.1, right? So you're going to have it's an accuracy is measured at a percent for a rated burden, because we said what are the two things that affect the CTs in a bad way? Burden, too much burden, and temperature, right? So those are definitely going to affect the ratings, and the nameplate stuff that we see on that CT is going to be burden and temperature. And you'll see that here in a second. So we can see that the burden definitely affects the accuracy of the rate, because it says, when it says on the nameplate, it says accuracy at a burden. So it's telling you at that burden what the accuracy is. So if you put too much burden on it, obviously that don't hold true anymore, right? Voltage rating is the working voltage can be applied to the primary and secondary sides of the CT. So as we said earlier, it's the voltage that the CT is operating at. Rating factor. So the rating factor determines the maximum current through the CT. It is a multiplier times the 100% rating, current rating. So as we just said a second ago, with the 100, we'll use a 200 to 5 example here. So I got a 200 to 5 CT with a rating factor of 3. Then that means I can actually load up to 600 amps on that CT and it'll still be fine. So as we've said before, now I can take a 200 to 5 CT with a rating factor of 3, and I can use it on applications all the way up to 600 amps. So I can use that one CT for a lot of different applications, okay? CT rating factor, according to Mr. Hudson, it is the most misunderstood spec. So the rating factor has absolutely nothing to do with burden. If a CT has a rating factor of 4, it means that at 30 degrees C, it can be used up to 4 times its label current and maintain its accuracy class. Notice Steve put the 30 degrees C. What did we just said? The two things, burden and temperature. And the temperature directly affects the rating factor, okay? And you can see right here. As I increase my temperature at the bottom, you can see my rating factor, okay? My rating factor, I start getting a derating of that rating factor, okay? When I get over here, you know, in like 30 degrees C, yeah, that looks good up there. I got 404 times. If I get out to 60, look where that 4 times has dropped. It's dropped all the way down to between 250 and 300. So if a CT has a rating factor of 4, it means that at 30 degrees C, says it right there on the nameplate, it can be used up to 4 times its label current and maintain its accuracy. So you can see right there at the bottom, it says CT with a rating factor of 4 at 30 degrees C, 86 degrees, is only a rating factor of 3 at 55 degrees C. See how much when I bumped up my current. So this definitely affects you when you're trying to design something out in the middle of the desert in Arizona, right? Versus in nice, cool, you know, mountains up here in Tennessee. So, yeah, it definitely affects the rating factor. So you have to consider that temperature, because you may get a derating and think you've got a rating factor you actually won't see out there at the site because of the temperature. Sizing CTs. Okay, so for best accuracy, a CT needs to be sized where the peak current falls between nameplate, current rating, and the rating factor. Because one of the cool things about this rating factor is when if I start adding and overload it, it's actually going to be, remember we talked about the bathtub curve where we had, as long as you were at 100% rating of that CT, the accuracy was 0.3. As soon as I got less than that, it was 0.6. It doubled the inaccuracy. It was twice as less accurate, from 0.3 to 0.6. But on the rating factor with these CTs now, as I go forward and I start adding more and I go 1, 2, 3, 4 times, guess what? I still maintain that 0.3% accuracy, which is awesome. So I can put more load on it and maintain it. So before when we said, well, at 100%, yeah, you get the 0.3, but anything less than that, it's half as accurate. No, now I can not only go to the 100%, I can go over that and maintaining the whole time that 0.3% accuracy. Okay? So let's look at an example right here. I got a 900 amp service. Remember the one from earlier? So I got a 900 amp service, and it would work best with a 300 to 5 CT with a rating factor of 3 to 4. So think about that. If I got a rating factor of 3 on a 300 to 5, 3 times the 300 gets me to the 900, and I'm still getting that 0.3% accuracy. So absolutely you would want to go with the 300 to 5 with that rating factor. And you can also get an extended range CT. So let's talk about that for a second. So I got the rating factor of, let's just say 4 on the 300 to 5. So I can go all the way up to 1,200 amps on the 300 to 5 with a rating factor of 4. But when I get the extended range CT, that goes the other way down to the low end. So here's what we're always fighting, right? We're always fighting. We have a city right down just south of us, small town. They used to make a lot of the seats for the automobile industry. So they're sitting there, they got these industrial sewing machines, this building's full of them, they're cranking all day long. Then that business goes elsewhere, now it's a warehouse, right? So now so those 800 to 5s now that are still on there, I don't have any load at all. If I had an extended range CT, it would go all the way back and grab them, because you can see there it goes all the way down to 5% of the nameplate, right? So whatever it says on that nameplate, I can go all the way down to 5% that low with the high accuracy. So I can go all the way down to the high accuracy, right, but all the way down to only 5% of the nameplate. So with one CT now, especially with the extended range, extended range CT, I can hit the low end, and then I get a rating factor and I can hit the high end. So that's where we're seeing a lot more now of a lot less CTs, particular ones being needed out there at the utilities. I can get one that'll cover an awful lot of stuff, right? According to Mr. Hudson, what is the number one most ignored problem at a meter site? Wait for it. The wiring. Okay? Why is that? Let's take a look. So bad wiring on the current circuit. So a faulty connection easily add a few tenths of an ohm of burden, either by improper wiring, improper connections. You know, if it's not connected up, if we didn't squeeze them on there tight enough, if I've got some missing commons, multiple grounds. Remember, we don't want to have multiple grounds in there if we can avoid it. So almost all wiring errors result in reduced billing. And you're thinking a few tenths of an ohm. So what? Well, let's take a look at that. So for 50 feet of number 14, you normally have, you can see the formula down at the very bottom of the screen there. So we're looking at the volume there at the meter. So we've got, so you've got 120 volts, right? And you've got a current of 0.2 amps. And I've got resistance there in back of 0.036 ohms. Okay, so that comes up with 0.006% error. But yeah, so no one should be upset about that. But wait a minute. What if we add through either a bad connection, wrong, too large a size of wire, we're talking about in a minute here, but you've added some more resistance in there. So now instead of 0.036 ohms, and if you've done a burden measurement out in the field with our equipment, these are the ones where you go, uh-oh, and that's where you see all of a sudden that you got way too much burden there, right? Which is resistance. So you can measure it with the equipment now. So I look in there, instead of the 0.036, I've got 4.036. That's 0.7% error. That is definitely a significant error. So if I have a bad connection, and those numbers do jump significantly. When you're out there in the field testing and you do a burden measurement with our equipment, you're going to see that. And when it's a bad connection, loose connection, broken wire, it doesn't just ease up a little bit. It will be a significant change in the amount of resistance, something similar to this, the good example Steve gave here. So now what about bad wiring on there using too small a gauge of wire? That's why we don't run 14 anymore, right? We run 12 and 10. It's because 50 foot of number 14 wire is 0.14 ohms of resistance alone, just the wire itself. And for a 0.1 class CT, you're already over it, okay? And 50 foot of number 12 has got you right there at it, okay? So that's why we've seen people go 14, 12. Now you're seeing so much 10 out there. It's because that gives me more leeway. I'm not already with just the wire alone being right there at the limitation of the CT, and I could possibly overburden it, okay? So you can see there at the bottom, see that without any bad connections or other problems, using too small a wire size can ensure you get the worst performance from your CTs. So you can see 50 foot of the number 14, I'm already jacked. I'm already beyond what I should be. And when I get to 50 foot of number 12, I'm right there at it, okay? So we've talked about that a lot, and this is another way that you can check the burden out there when you're testing with the equipment. Let's use a real-world example that Steve's got here. A sip of water. Oh. So we got a new service at Big Box Mart. Oh yeah, I've seen those Big Box Mart. So we got service configuration. We got a 3-phase 4-wire Y pad mount is a transformer we've got. The voltage is 27740 volt. So we got an expected, we got a max and a min on the load, right? You always look at what can we max out at and what can we possibly drop down to. Now remember what we've been talking about up to now. We've been talking about rating factors, extended range. So when you're talking about it, makes sense. We want to know what the minimum and the maximum is, right? So that we can know how we need to, what meter we need to have and what CTs we need to have, right? So we can start, the CT is definitely critical when we start talking about max and min, and we're talking about rating factors and extended ranges. Those are two critical things that we need to know, right, to be able to size them correctly. Pick the right one. So current calculation, we need to know that current. So you can take it's the power divided by the number of phases by the phase to neutral voltage. So remember in our example, the voltage is 277 volt phase to neutral. It was 277, 480 volt. So we've got, so it's 480 phase to phase, 277 phase to neutral. I shouldn't skip anything, sorry. And then, so on the expected load here for our max, we got 2,000 kW at my power factor on this is 85%, okay? So it's right on the edge of what we consider good or bad. And so our power factor is the watts over the VA. So all I'm doing here is I'm taking it from watts to kVA is what this conversion is doing right here, okay? So I'm saying, okay, so I go, the power factor is the watts over the VA, so the VA then equals my watts over my power factor. So I got 2,000 kilowatts over the 0.85 equals 2353. So my VA, my power there, the max there is, and I can look right there and say my maximum current now that I know that is, I can say it's my current, just you look at the formula up there at the top, the current equals the power, and we came up with the VA, right? We converted it from the watts to the VA to get our power. And so we've got 2353 kVA, so I got my power, divided by number of phases. This is a three-phase installation, and then it is my phase to neutral, not my phase to phase voltage that I use. So when I do all of that, I end up with 2,831 amps available there, max. So what kind of meter do we use? Remember where the break is, it's on the current, right? So we know that this is well over what we could use a self-contained for, the 2,831 amps. Right? So it says right there 400, and 400, you can say 400, there are 600 available, but so we'll say over 400, but it's definitely, this one's no question. So it's going to be a transformer rated. So, so the best meter, it would be a 9S here, and you can see where it's got the multi-range there from 120 to 480 volt, and it would be a 0.2% accuracy class. CT selection, here we go, that max min, right? So the max we said was 2831. You can see up top we calculated that. So what about the min? Okay, so we do the same calculations for the min and we come up with 180 amps. So I'm ranging all the way from a min of 180 amps all the way up to 2831 on the max. Okay? So 1,000 to 5 CT with a rating factor of 3 to 4, 0.3% accuracy at 0.1 ohm burden. Okay? Now remember, we said I've got 2831 is what I'm looking for, right? That's what I'm needing to be able to meter there. Well, guess what? And I'm needing to, so my CT should be sized off of 1,000 times 3 will get me to 3,000, gets me over my max. But on top of that, what does it do for me? Up at that upper end, remember I'm maintaining that 0.3% accuracy. Oh, once I get over 1,000 amps on that 1,000 to 5 CT with a rating factor of 4, we'll just say 4, then as soon as I get over the 1,000 amps, I stay 0.3% accurate all the way up, right? So up to 4,000. So in this case, you could get, like I said, you could get a 3 or a 4 rating factor on it, and it would cover you on the 2831. It would maintain that high accuracy for you. But we said this earlier, watch your temperature, okay? Because that could, so this is a great example that Steve gave right here, if you think about it. So 2831, if I had a 1,000 to 5 CT with and I had a rating factor of 3, that's 3,000, right? What if I had some of those what if I had the temperature influence it? I could get down below that pretty quickly, couldn't I? So what I would probably do in a high temperature situation, I might go with a rating factor of 4 to cover myself, okay? All right. So watch how the RF is affected by temperature. We just said that. If the CTs are mounted inside the meter can, yeah, in the middle of the desert in Arizona. I used to work jobs out there many years ago, and we literally put a giant thermometer out on a big asphalt parking lot out there in California. 135 degrees. Yeah, we melted the bottom of some of our boots got too hot. So it can get hot, and it will definitely affect the CT, that rating factor, okay? Use extended range CTs to get the best accuracy of max and min. So remember, if we got the extended range, it's going to go all the way back and grab them, right? So it'll go on 1,000 to 5. If I have an extended range, remember the 5%, it'll go all the way down to 50, okay? So I can go all the way down to 50 amps, so I definitely cover my 180 on the min side, right? So if I got a 1,000 to 5 CT with a rating factor of 4 and I had extended range, then I should be in good shape. Okay, PTs. We just did, like I said, we did the class on that earlier on the PTs as far as testing them and everything. They're like with us, almost, you never can say always, but almost all the time it's going to be step downs for us, right? So it says the PTs may be used to step down 40-volt size to 120. So in that case, you'd use a 4-to-1, so you'd get a fourth coming out of the secondary side on those PTs. So they must be sized proper for the VA rating, like we said. They go off of power. That's how they're rated. And as you remember, we covered that before, and they've got some of those the wacky designations, a little bit wackier. Of course, the CTs are a lot simpler than the PTs on how they designate it using the letters. But the PTs have an accuracy rating that affects the overall site accuracy. That's exactly right. Remember, I'm adding in the inaccuracy of the PT, but I'm also making it safer and easier to work with at the bottom of the pole. And they do add cost. They do add cost to the installation. So now wire selection. So if I have a secondary side rated for 20 amps, and I got 12, number 12 wire there, and you see how much there's resistance per foot with this wire. Hence what we talked about earlier about going from 14 to 12 to 10 now, right? So if you run a short run, remember it's per foot. There's a resistance per foot in wire. So the farther that I get, the more resistance that I've added. That's why earlier those 50 foot of a size of wire, 50 foot of number 14 in that, as I run the 50 foot, the farther I get away, the more resistance I'm adding, the more potential problems, because now I'm adding that burden, right? So you can see a short run of less than 25 feet, we should be okay, but what if the CTs are pole mounted? And that's when you get into the extended distances. So as we extend that distance, per foot distance, we add the resistance in there, okay? So, and we're talking about all of these different, you got the wire, you've got the CTs, you've got the PTs. So what you can look at, and you're going to have to when you're designing these sites, is the overall site accuracy, because you've got all the accuracy. I've got the accuracy of this component, I've got the accuracy of this component, I've got the wire between those components that's adding. So I've got to consider all of these things, right, when I'm doing this. So if you got the meter is 0.2% accuracy class, the CT is 0.3. So in this case, worst case scenario, you got 0.2 plus 0.3, so you're at 0.5 when you add those in. Remember, if you add the PTs in, you're going to add another 0.3 into it, okay? So I think this is a great presentation that Steve put together, and I think it shows that there are a lot of considerations when you're talking. I mean, you got not just, a lot of times you're just thinking about meters, CTs, and PTs. You got to think of the wire. You've got to actually consider the temperature. Okay, you've got to consider the distances you're going to run the wire. It adds the resistance in there. And all of these things need to be considered, because all we're looking for is the most accurate measurement of what's going on at that customer so that we can build them correctly, so that we can build them fairly both for us and for them. And if we're adding a lot of inaccuracies in there, what we don't want to do is design and come up with a site and then later have to come in and change it, and suddenly somebody's bill changes a lot because we didn't have anything, because we had something in there that wasn't maybe correct or the best component to be on that site. And when we do that, suddenly you got a little PR situation where I got to go to the customer and say, well, and that's not an easy one to explain. Now that we've resized things here, your bill's going to go up a lot. Those aren't the conversations you like to have with customers. So you like to talk about them expanding into new facilities where you're going to also, there'll be new customers for you. So it's very, very critical that you consider all these things. And Steve laid it out really well, talking about the meters, the PTs, the CTs, even the wiring. All this has to be considered when you're designing. And actually, too, and we know this, and now I'm talking to my peeps out there, and they can also design to be a little easier for us, right, to do some testing on. Because there's a lot of them you go out there and you go, I can definitely tell that guy that designed that site knew he'd never have to test this site, because you and I look at it and go, wow. So you can also make it easier on us. Anybody that's listening and designing these sites, help us out a little bit, us test folks. All right, so you can definitely make it easier on us by the way you design it. Much more accessible, easier to get to the bottom of the pole, but also the ratings and everything at the bottom of the pole. You can make it easier and safer on all of us. So, yeah, exactly. Please throw a test switch in there. Yeah, but we have meter adapters if you don't have one. I mean, I wouldn't do my job if I didn't tell you. So we have solutions for that, but boy, it sure makes things a lot easier, like Chris said, with a test switch. Yeah, put a test switch in there and size some things right for us, and it'll help all of us out, right? So upcoming on it, we've got the standards, traceability, and accuracy. Steve doing that one? Yeah, okay, so Mr. Hudson will be here. He'll do that one. So you'll have the smarts back in here doing that. And then next Thursday, I'll be doing billing versus the metering accuracy. So I hope you guys got something out of this. Any questions or comments? And if you noticed, by the way, I guess I should say, you noticed we used, you can't see them, but I'm looking that way myself. On our self-contained bench, we have lever bypasses on there to make that easier. So there's a good example of that over there on our self-contained bench. But yeah, you just, if you're involved in any of this, try and look out for us a little bit and help us out having to test these meters, pulling and putting these meters in and out. So just try and help us a little bit on our end because, in the end, we're actually watching out for the revenue for the utility company, all right? So we are the meter point and the revenue point, remember that. So thank y'all, appreciate it. And if you have any questions, holler at us. Please give us suggestions if you've got any ideas. And we'll also bring up that promo next week. And if we don't, I'll sure bring it up Thursday. And but thank y'all. God bless. Be careful out there, all right?